All right, let's get started. Is it extra dark in here today? There we go. Okay, cool. All right, so we've been talking about PCA for a couple days now. I seem to be really loud today. PCA are principal components we're going to use to do some sort of dimensionality reduction. One comment that we've had from a couple people now is that we're not really, when you rotate back, you rotate it into the new space, you eliminate some dimensions through a projection, and then you rotate it back into the original space. That original space is still going to be the same dimension, X had a dimension. After the rotation back and applying the principal components, you're still going to be in that original dimension. So you haven't actually reduced the dimensions that you're working in. You've sort of just reduced the dimensions that the data lies in. So conceptually, you've taken a d-dimensional space, you've squashed it down in this rotated space to be some smaller dimension. S is what we used for the nomenclature. And then we rotate it back, and we're still in a d-dimensional space, but we know because of that squashing we did, that projection we did, that that data lies sort of in a smaller dimension in the rotated space. So you don't actually end up with a smaller dimension in X, the original X. We'll talk about some techniques to actually get to a smaller dimension of X today, hopefully. In fact, I might even start with that. But let's just, before I start, I wanted to talk about homework 2 a little bit. A lot of people had some trouble with homework 2 from a perspective of we didn't see what we really wanted in the learning curves. And what I mean by that is I've had this graph up previously where if we're graphing some sort of validation set over time, and this is our accuracy, and this is our just time, represented, I think we represent it generally in, we do a sample every season, but we could do a sample every data point, we could do a sample, we can choose our, how often we look at that. So I drew this graph before that what you want to see is kind of this sort of pattern. If you have this sort of pattern, something is going wrong. If you have this sort of pattern, something is also going wrong. Now, of course, you can't know the scale of the accuracies a priori. So if we just change, if we only graph one of these, say we only graph the brown one, we could change the scale of the accuracy to squash that down, expand it out. We don't know for the data set how much that should be jumping around. Because we know that our approach is stochastic. We know there's going to be some noise. And just as we move the boundary around, we expect some noise as some positive and negatives come in and out of the the correct sets. So you can only really compare these to each other. You have to graph different learning rates, different lambdas, sort of thing, in order to get some comparison. Now, the downside of the homework, there was a couple, there was a general feel that they all came out as the brown line, no matter what you guys did. And part of that was the data set was skewed, and we had, I think, 75% negatives, and at best, most people were getting, at best, say, 82% accuracy. So really, we were only predicting a couple more positives or a couple more accurate predictions over just we could have predicted all negatives and gotten 75%. So by getting 82%, we only got a couple more. And when we looked at when we chose a really small validation set of only 50, that means that if just through random chance we add or lose a negative from the balance of in that set, we could be easily getting a noise of 2 to 3, or well, it would always be there's only 50 data points, so it would always jump in 2% increments. So we could easily be getting a noise of 4, 6%, and when you're at 75 or 80 and you're getting noise of that much, it's going to look like that brown line. So that was one of the problems. On next Tuesday, I'm going to try to put together a demo where we might look at some debugging techniques we could have used, things you could have done to, which would have been maybe different from what we suggested, but things you could have done to sort of debug if it was working, if things were learning the way you wanted. Generally, this is there's a takeaway lesson in that sometimes it's really hard to figure out if you're learning correctly, if you can do better, if you've just maxed out as good as you're ever going to get. That's a good takeaway for this assignment. It's not necessarily what we wanted you to get out of the assignment. One of the downsides of this particular assignment is that it was really easy to quickly get to a decent, sort of 80%. It only took a couple steps of the SVM algorithm to get there. And so we got there so quickly that you didn't see a good learning curve. Had you graphed a large validation set every step, you would have seen a better learning curve. The reason we didn't do that is because it starts getting computationally expensive, and we don't want you guys to get kind of hurt by the fact that you don't have super laptops or you can't get computational things. But had we graphed instead of seasons, had we graphed data points, we would have seen a slightly better learning curve, I think. So just commentary on that. If you saw a lot of noise, if you had trouble tuning your different parameters, that's probably not unexpected. A lot of people had that problem. Now, you should have gotten into the 80%, it seems like, although there were a group of people who never got up there. And I haven't looked at their homeworks to see if there was something wrong or if there was just bad starting points in the SVM algorithm, or if there was something weird that was causing that. At least one of the TAs had that problem when he was looking at the assignment, where he actually had trouble getting this to learn in a proper way. So don't be too worried. We don't grade on accuracy. We grade on properness of the code, usually, whether you implemented the algorithm correctly. So if you didn't get a good accuracy, don't worry about that. But like I said, we'll try to look at something next Tuesday if I get around to making that demo. And hopefully that'll help you guys understand how to debug this stuff a little better. Okay, back to PCA. PCA is, we've talked about it as a dimensionality reduction, but we project it back to the original dimension. So it's useful. It cleans up the data some. We're still going to have trouble viewing it using a direct PCA, so we're going to do some other things. But before we do that, let's just look at the methods that we talked about to get our principal components. The first one is just decomposing the covariance matrix using a pretty standard eigenvector decomposition. The downside of this method is that the covariant matrix can be very expensive to compute and can have very low sort of accuracy, because you need a certain number of data points in each dimension. Like if you have 100 dimensional feature space, you need 10,000. You have 10,000 things to compute, or 5,000. That's the right number. Yeah, 5,000. So you need some amount of data to actually even get those accurate. So if you get up to really high dimensional spaces, for example, our image space, you end up with needing a lot of data to get those dimensions accurately calculated. So in general, not only is it computationally expensive, it has an accuracy issue. So then we talked about if we want just a couple principal components, there's a method that we can use called NIPALs. So NIPALs, what we start with is we're actually going to learn the W's that are associated with the first principal component only, and U, which is the first principal component. So we're only learning a single principal component here. And we do it, instead of using a matrix decomposition, we do it in a much more direct fashion where we do a minimization problem to find U and W. So we went through a bit of math, but what we came up with is that we're going to start with some U star, and typically we'll just choose one of the X's from the data set. Because that at least is in the right ballpark for something in the data set. We're going to take the W, for this whole thing, we're going to assume a mean of 0 for the data set. Most of these techniques assume a mean of 0. We know how to do that trivially to move it from the original mean to the mean of 0. So that happens here too. We're going to want a mean of 0. But we're going to start with some U star. We're going to calculate a new W. That new W is just going to be the data set times U star over U transpose U star. Sorry, those are all starred. And that'll give you a new W. And that's an estimate of W. Then given that estimate of W, we can get a better estimate of U through the U star equals X transpose W star transpose W star. That'll give you a new estimate of U. That U will probably be poorly scaled. We want our eigenvectors to be unit vectors. So we're going to rescale that unit vector just to make it or rescale that U star to make it a unit vector. At the same time, we have to rescale W. Now, when you're doing the iterations, you don't need to rescale W right away, because you're going to calculate, each iteration, you're going to calculate a new W anyways. So it's going to get, the scaling doesn't matter as you're running the algorithm. However, at the very last step, when you're going to stop finally, if you rescale U, you have to rescale W by the inverse. So you only need to do that at the very end just to make sure that W is the right scale. And that's, in case that wasn't clear, when you rescale U, you're going to skip to the W star calculation again, typically. So you kind of throw out this W that you have at that point to calculate a new one. So that's why you don't care about rescaling it. It doesn't really matter if you rescale it. It's not going to be an efficiency issue, most likely. So now I think we didn't really talk about the stopping condition. Remember, the X hat is equal to UW transpose. That's our new estimate using only the first principal component. And what we want to do is we actually want to check what the distance is between X and X hat. So we just look at the distance. When that distance gets small enough, we stop and we say that we're close enough to have the real principal component. Now that small is, what's up?
Is X hat supposed to be W star, U transpose star?
Yes, these are the estimated ones. Yeah, that's sort of implied. It's what we come up with in the end.
I'm sorry, what does scale W star by inverse?
What does what?
What's the inverse of W?
Where do we ever take the inverse?
Normalized part?
Oh, this guy. Oh, you're gonna scale U by some scalar S, and you would take W by 1 over S.
Okay. Oh, because when we normalize U.
Yeah. They have to be. I mean, you're gonna multiply them in a second, so you can. I mean, if.
Okay, I
WU transpose is equal to S over S U or WU transpose. So you're going to want to take 1 over SW for whatever the U transpose is.
And S is not necessarily the norm of U.
Well, it'll be the it'd be the norm of U because it's the norm of U because you have to get it to be it'd be 1 over the norm because you want to get it to be a unit vector. Sorry. Okay, so anyways, to stop what small is considered, you're looking at 1e to the negative 5 maybe. It just depends on how much precision you need in your eigenvector calculation. But it gets this technique has a tendency to get pretty small pretty quick. Like it converges fairly quickly, so you don't have to run this for a huge amount of time. It quickly gets down to a pretty small error. And remember, there will always be an error here because we're eliminating a lot of information when we're taking only the first principal component. So maybe is small is probably not the right thing to do. It's more of as the delta from the delta error from iteration to iteration gets small is probably more what you're interested in. So iteration 1 versus iteration 2, you're going to get 2 different estimates. When those things kind of converge to be the same thing, that's when you would stop. Otherwise, you don't really know how much error you expect in those values. Okay, so NIPALs, that's only going to give you the first couple principal components. It'll give you the first just by doing exactly what we said. To get the second, you subtract the first from X, then you estimate based on that, and you can get a couple principal components that way. Quickly, you will accumulate numeric errors doing this, and those numeric errors will make it so that this is not a stable process to get eigenvectors that are far into the the range. So 5 eigenvectors fine, 50 eigenvectors not going to work. So we don't want to calculate the covmat of X. So we got another technique that we can use, and this is going to rely on our singular value decomposition. Singular value decomposition is another standard technique that any linear package will have. Just like eigenvector decomposition on a symmetric matrix, you could do a singular value decomposition. The nice thing is you can do it on any matrix, and it'll give you a set of what they call the singular values. So what you're going to get is if you take our original data matrix, a singular value decomposition is going to give you some U sigma V transpose. Now, both of these are orthonormal, which, if you remember, that just means U transpose U equals the identity, V transpose V equals the identity, and we have the inverses are equal to the transpose. All of the vectors in there are going to be orthogonal to each other. This is going to be diagonal. Now, given this, we can replace the X with the SVD estimate. So if we just if we're talking about the covmat, this is equal to X transpose X. If we were just take the X transpose X, and we substitute in this guy, we're going to end up with V sigma transpose U transpose times U sigma V transpose. My marker seems to be dying there. The U's will cancel out, and you'll end up with V transpose sigma, sorry, there should have been, nope, the V transpose is at the end. So V sigma transpose sigma V transpose, and that is going to be equal to, sorry, I lost it. Is going to be basically the equivalent of the X transpose X. So now we can use this just like we used the covariant matrix. We can use this set of things which turn out to be the eigenvalues. And using those, we can do the same process we did before. These end up being actually the eigenvalues. These end up being the eigenvectors. Sorry, I misspoke earlier. And you end up with just using these as your principal components and these as your eigenvalues. Actually, for what it's worth, it actually comes out that the eigenvalues are equal to 1 over n. There's a scalar in there that we dropped when we were doing the math. So this is really easy. You can just do the singular value decomposition. You end up getting this V sigma U. You take the V as your principal components. You'll do the projection just like you did before, where you drop some number of those principal components, and then you can rotate back into the original space. So this is sort of a quick way to do this. It is substantially more efficient versus finding the covariant matrix and then doing finding the eigenvectors. Just forgot what I was going to say. Must not have been too important. So this is just the way that you normally would do this. And it's going to be more efficient. It's going to be more accurate. It will give you all of the eigenvectors. Most linear algebra packages will allow you to ask for only a subset of them. So you can ask for only the first 10, and it will figure out how to get those first 10 for you, either through an iterative method like NIPALS or through other methods that the singular value decomposition uses. All right, that's going to be, oh, I know what I was going to say. This all assumes, again, we're working with a zero mean X. If you do the singular value decomposition on a non-zero mean X, it will give you something. And it will look like eigenvectors, but they will not be the principal components. So again, you have to zero out the data set, and then later on you'll add that mean back in to get to the original space. But assuming you had a zero mean, then these are the actual principal components. Any questions on that? All right, cool. That's going to be pretty much the end of our principal components. Okay. Now we're going to go and we're going to talk a little bit about how to visualize data in a low dimension. So the principal components, they were useful in some ways in that they compress things, and you can view them. Sometimes it makes sense to view the principal components in the high dimensional spaces. Like when we look at faces and we're looking at images, it's okay to look at those principal components in the high dimensional space. But a lot of times we don't want to sort of visualize components in a high dimensional space. So we're going to look at a series of techniques, two specifically. We're going to look at one today and one on next Tuesday probably, that are going to try to visualize data in a low dimensional space. So the first one is called multidimensional scaling. And the idea behind multiple dimensional scaling, or MDS, is that you're going to take the x's, which are in some high dimension, and you want to translate them into some low dimension that you can actually view. So usually when we're talking about low dimension, we're talking about 2 or 3 dimensions. That's pretty much the most that we can view on any sort of graph. Now the way that MDS is going to work is that we're going to try to do a projection such that we maintain the distances between points. So in the high dimensional space, points are arranged in some way where each point has a distance to another point. And we're going to try to preserve those distances so that in the low dimensional space, the points are sort of arranged in the same way where things that were far apart in the high dimensional space remain far apart in the low dimensional space. Things that were close in the high dimensional space are close in the low dimensional space. To that end, we're going to need to measure our distance. So we look at some dij of a data set. This is going to actually be, this is the data set, and then we're looking at the dij, which is the actual distance between 2 specific elements. This is going to be the difference between the 2 transposed times the same thing. That's just the distance formula. This is actually the square distance for what it's worth. I think the book puts a little 2 up in the corner to let you know that we're talking about the square distance. We don't really care that it's the square distance. There is a downside to using the square distance, which is that it's going to work a lot. It's going to spend a lot more effort trying to get the things that are far apart correct, as opposed to the things that are very close. Because we're going to try to reduce, get these distances to be about the same, but we're going to use a square distance, which means that when things are really far apart, you pay, the square of that cost. So that is a problem with MDS that we're not really going to look at. In the next technique that we look at, it tries to avoid that. But just know that MDS does have an issue with that. So what we're going to do is we're going to try to minimize a expression which is the sum of the data points, and we're going to have some distance between the data points in the X original space, and the distance between the data points in the Y space, and we're going to take the square of that. And we're going to try to minimize that particular expression. Now, we're going to assume a zero mean again, just because it makes it a lot easier to look at everything in the zero mean. But there's a proposition I have here that if we look at X transpose, what's up?
So what's X and what's Y in this case?
X would be the original data set. Y would be the new data set that that is represented in a small dimension. So the Y is going to be, say, 2 dimensions, and the X is going to be the original D dimensions. And then we're going to be able to, plot the Y where you can't really plot the high dimensions in, for most data sets. Make sense?
Yeah.
Okay.
And when we're doing the distance, like the distance of Y, what are we comparing? We're comparing like how
So if you think about it, in X, you're going to have 2 points. They're going to have a distance between them. In Y, you're going to have those same 2 points, corresponding points, and they're going to have a distance between them. So Y to Y versus X to X. And we're going to try to get those things to be close to each other. So X10 to X15 is going to be a distance. Y10 to Y15 is going to be a distance. And we're going to try to get those things as close as possible, those distances as close as possible. Okay. So this is sort of roughed out in the book. But there's a claim that if I get XXT close to YYT, that's going to imply that the distance between the X data set and the distance between the Y data set is going to be close. I'm not going to show that here. It's not very informative to look at it, but it is true. And if we know that, we're able to actually do the minimization. So we're going to try to find some. Let me put this on the next page here. Okay, again, we're trying to find some Y, which are a bunch of things, Y1 down to Yn, where each of these Y's are the low-dimensional space, so 2 or 3 dimensions. And we're going to try to find that. Again, that's such that Y is some low S-dimensional space, and the distance between xt and YYT, is minimized. So that's the problem we have to solve in order to do this. So again, SVD is going to be the technique we're going to use. So if we look at SVD, we know that X is equal to some U sigma VT. Now we can project out some of those dimensions, basically just drop them. If we take all the sigmas, which are basically scaled versions of the eigenvalues, and we zero out a bunch of them, we can get a new data set that is US sigma S VTS. And all we've done there is we projected out a bunch of the dimensions. We just dropped them. Now you have to drop the right ones. You drop columns in one case. You drop basically rows in another case. And you shrink the sigma. The sigma, remember, is diagonal, so you take both the dimensions smaller. So you got to do it in the right way to just do that. But that's basic linear algebra. And then we're going to define, or we can look at SST. This is going to be sorry, I was just confirming that that's in the right order. It is. That was not what I was expecting. So this, we're just plugging in this for this. We end up with this expression. Then if we take y equal to s sigma s, we end up with some YYT equal to XXST. And that, if we look at the error between X transpose minus Y, this is the problem. These are supposed to be this. I apologize for that. That's why my math was coming out incorrectly. YYT. This is, again, what we wanted to minimize. This is actually equal to the distance between the original sigma squared and the sigma s squared. So, why do we know that this is the smallest distance that we can get? Well, we know that these are, scaled versions of the eigenvalues. The eigenvalues are arranged from the largest to the smallest. So if you want to get the smallest amount of error between this and this, you drop the smallest elements. So if you drop all the smallest elements, you're going to get the smallest change. And so that means that you're going to get the smallest of those. If you get the smallest of those, just by that conjecture I put out there, you'll have the smallest distances. So does that make sense? So that's kind of going to be the very straightforward technique we're going to use. We're going to take X, form the SVD, drop a bunch of the things, a bunch of the dimensions, and we're going to end up with a Y based on that.
How is this different from PCA then?
This is actually coming up with a lower dimensional representation that we're going to use. Let's see, how is this different? So the question is, how is this different in the rotated space than PCA? PCA doesn't try to, in any way, try to maintain distances, but you end up with approximately the same thing. I would have to think about that. If this is, under what circumstances this would be PCA, a low-level production of PCA. I don't know off the top of my head is what it comes down to. Yeah, sorry about that. Does this technique make sense so far? Okay, cool. So there's one more thing that we want to look at. We were, move those over there. We originally were talking about, this is just what I wrote out previously. The distance of X is equal to some where did it go? Xi minus Xj transpose, and then the same thing, non-transposed. Now, if we multiply that out, we can actually get the distance of ij of x equal to some x transpose, sorry, this is I minus I transpose xj plus xj transpose xj. That's just a multiplication of that product. So pretty straightforward. Now, what we're going to do is we're going to do a little odd transformations here, and it's not going to make any sense until we get to the end. And now that I think about it, I'm not sure why I even need that. I'm going to have to look in the book to see why we need that. A, we're going to define a matrix A. A is going to be the identity matrix, and then that's going to be slightly changed by the 1 over n I, or sorry, this is an I. This is the one vector, so a vector of all ones, and then the outer product of all ones, which ends up with a big square of all ones, a matrix of all ones. That's just how the book writes it. I would have just written an n by n one matrix. And then we're going to define that, and I'm not going to prove this, but we're going to say that a distance of x, at, equals x transpose. If we do that, we're going to be able to do some interesting math. This is proven in the book. A lot of these steps are proven in the book. They're not important to really understand the technique so much as we just want to lay out the rough outline. So we're going to call this guy W, and then we're going to claim that W U equals U sigma. We're going to take Y equal to the US, the projected sigma 1 over 2. And this is going to be our new Y. So basically, we're going to take this W, which is defined to be this. We're going to find the eigenvectors of that using a eigenvector decomposition. And then we're going to just define Y to be that the eigenvectors of those low number of dimensions. These guys end up being the scaling that we need is actually lambda of the square root of the lambdas in order to get the scaling correct. Now, this technique will yield the exact same thing as this answer right here. These are both going to be lambda value, or these are both going to be eigenvectors. This one is going to get to it in a different way, though. The nice thing about this technique, which is slightly different, is we never need to know the actual data. All you need to know for this version of it is the distances between the pairs. And there's actually data sets out there where you'll have a bunch of points, and the points will just have the distances. We won't know things like the exact feature values. We'll just know that things are sort of certain distances away from each other. And so let's look at an example of this. Why this is useful. So this is actually a map. This is a map of South Africa. And what we have is this is the real map over on the left. And we have a bunch of cities defined here. We take these cities, we know the distances. So based on the distances, we can use... Is there a question?
Yeah, can you go back to the previous?
That guy? Is this sigma, which sigma? Yeah, this is going to be the equivalent of the sigma. It's the square root of, it's the squares of the singular values. Yeah, of x, yeah. Yeah, I think that's right. I'd have to double check the math. Because there's this A, because we have this A, that A in there, I think those are, I mean, certainly these are the singular values of W, not of the X. So you're actually looking at, so we define this new W, which is actually this guy. I actually am not so certain that this is correct, so much as that's correct. I think we can get this that it's implied based on this down here, but I would have to double check the math on that. Yeah, X transpose. Yeah, I'm a little. Well, it's because it's the question is if we multiply through by the A and the distance we know is X transpose. Does A cancel out? And I think it might, but I'd have to double check the math. But the point is, we never, with this technique, okay, we didn't need that equation. With this technique, we only need to know the distances. We don't actually, that's why we don't really care if that equals XX transpose, because we're not going to take advantage of that. We want to take advantage of the fact that we only know the distances, and those distances, we never need to know the original features. And that's what makes this technique a powerful technique. So let's go back to the example. So this is the example. This is a pretty good example, actually. You often, I mean, we obviously could know map coordinates, and we could do the x transpose to get all the distances. However, we could also just take a list of distances between cities. And if we just took those list of distances between cities, we could get recreate basically a mapping in 2 dimensions of the sort of layout of those cities. So if you look at this, on the left is the actual South Africa. And David, I believe, is actually from South Africa, which is why he chose South Africa. You actually get the layout here, and the MDS is the one on the right, where we basically recreated this. Now you have to, once you recreate it, you have to rotate it so it's sort of in the same orientation to look at it. But once you rotate it, you can actually see that, you know, Cape Town is down in the corner like it's supposed to be. The Pretoria is up, not on the other map for reasons. I don't know why he dropped that. Let's take a different example. Which ones do we have? Johannesburg is right where it's supposed to be, sort of thing. So you can see that it laid it out in approximately the same orientation, which is what we wanted from MDS. So is there any questions on that? That's pretty much the MDS technique. Now on Thursday, we're going to look at something called TS&E. I didn't get around to prepping the TS&E text, so I didn't want to go into it today. It's actually listed or in the book way at the end for some reason. But it's a visualization technique that works very similar to this. And so I'm actually going to take it and move it forward, so we're talking about all the visualization techniques kind of in the same time. I don't think it actually requires to be that far back in the book, and when I taught it last semester, I'm not really sure why. I couldn't figure out why he taught it so late. So anyways, but I didn't get around to it today, so we're going to move on to a separate topic just to fill in, and then we'll jump back to the TS&E on next Tuesday. So we're going to talk about a brand new technique. This is actually another chapter. I think it's chapter 8. And this is a somewhat interesting technique that has a very different use case from the things that we've been looking at so far. It's called canonical correlation analysis. And canonical correlation analysis is it's very different from what we've been doing. It's taking 2 data sets that are paired. So we're going to look at a data set xi, and it'll have a corresponding data set yi. And so you can think about this, a good example, and one that we're going to look at actually in a little bit. We'll probably run out of time here, but when we get done with this, we'll look at this example. Let's say you had a set of images, and for each image you had a description. Now those images and descriptions are in very different spaces. The image is some set of pixels, or possibly some description, some extracted features from that image. The description is going to be some set of words. They aren't going to be in the same feature space at all. So if you come up with a new image and you want to get a description for it, you won't be able to just sort of do that translation directly. So we're looking for a technique where if we have a pair, a bunch of pairs, so an image and a description of that image, we can project them into the same space, and then once you project them into the same space, you can make comparisons. So you can say, I get like a new image, and I want to find the description. So I take that new image, I take that projection that I've built, and then I look at the projections that the other Ys have, and I can get kind of the nearest neighbor to pull out a description of that new image. So that's going to be kind of the technique that we're going to use. We're going to map from some X to some Y, where they're both going to be multiple dimensional. And that's really the big difference, is they're both going to be this will be some D dimension, and this is going to be some D2 dimension. Not D squared, but some other dimension. Okay, so we're going to call, we're going to learn two vectors, U and V. And those are going to be the projections. Now, these are going to project just into one dimension for now, and then later on we're going to find multiple of these to have more dimensions. But what we're going to look at is some U X and some U transpose X, and then V transpose Y. And we're going to try to reduce the distance between those two things. So we're going to project them both into this shared space and then get them to line up in the same spot. And the way we're going to do that is we're going to try to, I misspoke there. We don't need them to be in the same spot so much as we need them to be highly correlated. So we're going to try to make it so that these two projections in a linear space are highly correlated. And that's going to be the technique that we use. We're going to look at the correlation of these projections, and then we're going to determine a U and a V based on that correlation. So just an aside here, if we are to look at the covariance matrix of P, and P is PI is the Y and the X just concatenated. So they're actually there's actually a transpose there. Sorry, if we transpose. It's a column vector of all the values, just to get it right. So you have all the X values, you have all the Y values. They're all concatenated into a single column. If we were to look at the covariance matrix of P, which is just the data set composed up of all those data points, it's going to look something like this. It's going to be divided into 4 parts. Up in the corner, that's going to be the covariance matrix of XX, and we're going to write that sigma XX. Down in this corner, that's going to be the covariance matrix of YY. And again, you can just do the linear algebra to determine this. If we were to write out the whole definition of covariance, it just falls out of how all the matrices get multiplied. And then in this corner, we have the covariance matrix of the Y's versus the X's. And this guy is the X's versus the Y's. So that's kind of the breakout of the covariance matrix of P. And we're going to take advantage of those different covariance matrices to calculate the correlation between these projections. So what we want to minimize is going to be the correlation between the U transpose X and the V transpose Y data sets. This is going to be just equal to the covariance between U transpose X and V transpose Y. Remember, this is set up so that these are both scalars. Sorry, that was. I didn't mention that, but the Y, the U is the same dimension as X. The V is the same dimension as Y. You take the dot product, you end up with scalars. So we're taking the covariance of two scalars. And then we, to get the correlation, we have to normalize by the variance of those individual things. So we take the variance of U transpose X, and then we take the variance of V transpose Y, and we end up with the correlation. And we want to minimize this particular thing to find U and V. So we're going to find U and V such that this is minimized. We can rewrite this in matrix form as U transpose sigma xy V over U transpose sigma xx U and square root of V transpose sigma yy V. So now we need to find something that minimizes this. Now the interesting thing about this is that these two things are constants. If we knew y and we knew v, those become constants. So allowing those, if we knew those to be constant, if we assume they're constant, we can rewrite this problem, this minimization problem. Actually, sorry, we're going to try to maximize the correlation, not minimize the correlation. Minimizing the correlation would be an anti-correlation. That would be a bad thing. So we actually want to maximize this, not minimize this. So we're going to maximize this. We're going to try to maximize this U transpose y v under the constraints that U transpose sigma xx U transpose is equal to some constant 1, V transpose sigma yy V is equal to some constant 2. Now we don't know those constants. We're gonna figure them out eventually, but we don't know them up front. So this next step, we're going to use sort of an optimization technique that uses Lagrange multipliers. If you don't know what a Lagrange multiplier is, don't worry about it. It's just a numeric technique to do optimization. But we can rewrite this maximization problem slightly using Lagrange multipliers. So we're going to try to maximize the U transpose sigma xy V. And then this is where the Lagrange multipliers come in. We end up with U transpose xx U minus C1 minus, sorry, these are over 2 just to make the math nice. V transpose sigma y V minus C2. So that's what it comes out to be. Now we need to minimize this. We're going to minimize this with our standard technique where we're going to take the derivative of this, set it equal to 0, sorry, we're going to maximize it, not minimize it, but this is going to be, we're going to need the gradients in order to calculate that. So the gradient with respect to u of this whole thing comes out to be v minus and we're going to set that equal to 0. The gradient with respect to v is very similar. It's sigma transpose xy u minus 2yy v, and we're going to set that equal to 0. So now we just need to do some manipulation, algebraic manipulation. We can solve for u from that first one. Solving this equation, which we call equation 1, we end up with 1 over lambda 1 sigma xx inverse sigma xy v. Then if we plug in the value of u into equation 2, we're going to end up with, they start getting really long, sigma yy inverse, sigma xy, sigma xx inverse, sigma xy, v equals lambda 1, lambda 2, v. Now, that formula right there is very similar to something we've seen before, which is the eigenvalue decomposition. This guy we actually know is symmetric, which is why we could take the inverses, because each of those pieces were symmetric. And so we're trying to find some vector times some set of values, which is going to be some eigenvector decomposition. Similarly, just so we have it here, we can find the u what am I doing on time there? Oops, sorry. This is y. Okay. Now this is actually going to be a set of eigenvalues. That's a whole vector, not a scalar. So now it's just a matter of plugging into that original correlation that we were looking at, which is this guy right here. From this, we can formulate each of these guys, and we can extract the actual values that we need. The book is going to talk about that. I'm not going to do it just because it's just a bunch more math. And when you need to do this, if you need to do this, you just have to follow the formulas. It comes up with a bunch more formulas. But in the end, what we get is some v and some u, and we get the set of eigenvalues associated with those. Now, we don't care what those lambdas are. All we care is that they're ordered. So in the end, we're going to select some number of v and u, some number of eigenvalues, and we're going to use those as our transformations. So if we go back to our original x's, we'll have an xi. We would take a u transpose times xi. The first new feature in our data set is going to be the first eigenvector. So we're going to sort of project into a new space, and this will be the first value. And then similarly, the v1, which is the first eigenvector of that we found right here, times the y, that's that, That's going to be the first element of our projection into a new space. And you can do U2, xi, v2, y, transpose. And you can just line these up until you get some, again, some S number of them. That's going to be our x vector. This will be our y vector. There's an S down there, y, I. And so those are projected into a new space. So if I know my x, now I get projected into this space. Once I'm in this space, I can look up sort of the y's that are closest to it. Once I find the y's that are closest to it, I would return that as sort of the mapping that I was going to use. Let's look at an example of this. And hopefully you guys can see this. Let's see how big this is. Well, that's really hard to read. Let's see how much we can zoom that. Okay. Okay, so this is exactly what I was talking about earlier. Okay, that went way too far. So we took some images, and we took some description. And I believe in the true are in the red and the predicted are in the green. So here's a train. For some reason, the train was labeled as a tree, which presumably they're talking about the tree in the background. And using this technique, we can look up the y value that's closest. So we end up with tree coming back out. Now these the y values are just going to be bag of words. We haven't really talked about representation for words yet, but bag of words just means that each word in your dictionary is going to have a, basically, is it there or not? So all the words will have, like, it'll be a vector of 0, 1s for each of the words that are there or not. So in this case, it would be a 1 for tree and a 0 for all other words that are in their dictionary. So we see a tree, that's good. Over here, we get a fairly reasonable, it gets, some set return that probably is close. The table's there, man's there. It's possibly a classroom, so it kind of returns some that wasn't in the original, but are probably pretty logically close. And this y is actually, or sorry, this number at the bottom is actually the correlation that we calculated. For this guy, we end up with, it has a house and a tree. It only caught the tree. This guy, it came tree and trunk. It only caught the tree. Now that's probably okay. All of those are actually really good examples. One thing you'll find in these sort of data sets where you describe stuff, often they give you partial descriptions, or they give you extra words. You don't always get the right thing back. So these are all really actually good mappings. These are some bad mappings. So you have some big description here, and it thinks it's a tree. So that's actually a pretty bad one. Another one, it has some big description, and it actually came up with the same mapping as this one did up above. So you're returning whole, because you're doing nearest neighbor, you're returning a whole vector of y's that you've seen previously. So this was the vector that was closest to this. Now the nice thing is you can judge how good it was by looking at this number here. So you could kind of figure out whether it's good or bad. These are some even worse ones that are just basically, they just didn't work at all. So that's kind of the technique. Canonical correlation analysis. Again, it's a technique you use when you're mapping from a sort of D1 dimensions to a D2 dimensions of two different things that have pairs. And it does actually work pretty well for some data sets. It works very poorly for other data sets. The reason it works poorly is because of these guys down here. If you're trying to sort of maximize your correlation, you can instead maximize the variance of those individual things. So if you, minimize them. You could choose the lowest. There's a lot of people waving, so it must be important. All right, I'll underline them again. These guys, if we're trying to maximize this guy, we can minimize these guys. So you can actually select the things that are basically noise, the dimensions that are basically noise to generate these values. So that's actually a problem with this technique. Is sometimes you'll basically come back with results where there's no real correlation. It just shows dimensions where there was very little variance there. So at the end of the book, on this chapter, there's a technique for actually double checking that there's the correlation that you wanted. So basically you run the technique, you get back some vectors, and then you run this technique that basically checks the correlations, make sure they're there, make sure we didn't just get some spurious results. So that's pretty important when you use this technique, to double check always your results. And if it doesn't work, it doesn't work. There isn't really a good solution once it doesn't work. We'll look at later on, we'll talk about some other solutions to solve problems like this, but they're fairly advanced into the neural network sort of realm of things. So neural networks can also map sort of arbitrary to arbitrary things, and we'll look at that later. So that's all I got for today. Any questions? Okay, I will see you guys next Tuesday.